Can you hear me? Okay. Well, this is a talk about memory, and I'm one of the maintainers of various components of the memory management subsystem in Linux. And so this is the perspective of the one who actually has to make all this stuff work with the operating system. We've created a new type of memory, actually we have gotten new types of memory from the manufacturers. And so I want to discuss these new types of memory, how they can be managed, how they work, and what happens if you use RDMA on them, or how do you actually use RDMA on these types of memory. This works or doesn't? So what I want to do first, give a brief review of the traditional memory subsystem and how we saw memory in the good old days when things were simple. Then we will talk about the new features that were added to Linux memory management subsystem, and what kind of exotic stuff is available now, and how do you actually work with these new subsystems. And then I'm going to give a kind of a short, brief overview where I wish things could be going, where I hope things could go in the future. And if you have any questions, I'm ready to take them at any time if you want. If you want me to expand on a subject matter, we can do that. So traditional memory. In the very beginning, we had memory with uniform access. So accessing any memory location in your system would have the same latency. That caused problems initially when we ended up with devices that were not able to access the full physical memory. So then we started segregating memory into zones. There was a zone for the devices that could only do 16 megabytes, and a zone for the devices that could only do 4 gigabytes, and then a zone for the whole of memory. So that was the first categorization of memory in Linux. Then came the new architecture here with multiple sockets with memory that is closer to one process or another, depending on the processors. And then memory accesses became non-uniform. So this is a 2-node system up there, and a 4-node NUMA system down there. With that came new complexities. Now we had to consider where to allocate memory from in order to have the fastest performance of a process. So the system now has a table that describes the distances to memory, and we have to work with that. With that come memory affinities. So which one is closer? And the system makes intelligent decisions and tries to guesstimate where you would like the memory to be. If you don't want that, you can specify memory policies. You can override how the default behavior of the system and tell the system, I want memory from that node because I know my process was going to migrate there or something. Then further on, there came CPU sets. You had the ability to restrict applications, groups of processes to a certain NUMA node and to a certain processors on the NUMA node. Then we evolved that to C groups, and this became the containers, which can control much more than just memory. And it's very fine-grained too. Once we had the performance issues, a process could be distant from memory. A process could be running on the left side, but accessing memory from the right side for some reasons. And you want to change the situation. Then we get the need to have process migration and memory migration. You can migrate the process closer to the memory allocated, or you can change the memory as to where it is located. So the system copies the memory to a different node and makes sure it is in the NUMA node you want. With that, we are able to change the physical memory underlying a process while the process is running. And then we had, we started also having RDMA back in 2004 or 5. And RDMA to all of these types of memory is not a problem. What we do when we register memory is we pin the memory. This means at that point, memory migration and swap and all these things are disabled. And the RDMA subsystem ensures that memory stays pinned in a certain range. This is pretty important. The memory becomes unmovable. And if you do that with large areas of memory, then the operating system can no longer swap pages. And if you have the right load, the thing will just keel over because there's no longer enough memory. So we have all sorts of protections there as well. The RDMA performance varies depending on what NUMA node you go to. If your NIC is on the left side, the RDMA NIC, and you're transferring to the right side, the performance will be limited by the additional overhead created by the interconnect. So there's performance issues there in this scheme. So that was the good old days. I think this is pretty simple, right? Let's see what all the stuff that we've added over the last years. First of all, we added new memory zones. We wanted to make sure that there's sufficient movable memory in the system, so that you can create larger contiguous segments of memory. And so you can define a portion of memory to be movable. This means no allocation will take place in that zone that would not be movable, and therefore you are able to relocate all these objects so that you have a contiguous segment of memory if you wanted to. Then we get an innovative use of NUMA nodes. For example, one vendor used HBM and defined HBM in a memory as a memory node, additional NUMA node that had no processors. With that, you are able to target allocations to your HBM node, and you can then code your apps so that they can exploit the characteristics of HBM memory. Then there arrived other types of memory nodes. Some institutions need extremely large amounts of memory. And so you could create a system with 100 or so memory nodes and just a few processing nodes if you want to keep an extreme large data set in memory. And then there are also the memory-less nodes. Other use cases involve a huge amount of processing, but they don't really need that much memory. So the other configuration also exists in HPC. And some of them are even created in nodes where you just have device memory. Then we have some advanced memory features these days. There's AutoNUMA. This means the operating system determines from your access patterns if the access patterns are optimal. If not, it will move the physical memory closer to your process. And it does that while you run automatically. You don't need to manually move memory anymore like you did in the good old days. And we have transparent huge pages. The operating system will scan your memory of the process and figure out if there's anything contiguous in maybe 2 meg segments. And if so, it will use the automatic memory migration to migrate all the pages to be contiguous and give you one contiguous 2 meg page. And then we had on-demand paging for RDMA. At that point, we don't have to pin anymore. The danger of out of memory is avoided. And we can register large amounts of memory for example, the complete address space of a process, which makes it much more easier. And this can be used to move the memory registrations out of the critical loops. Then we have the, this is duplicate, I already talked about that. Then we have non-volatile memory. So we've talked a lot about that, so probably some of that is duplicate. So you can use it like regular memory. But now we have new challenges with data consistency. And so the typical use case that we see with non-volatile memory is to handle it like a regular block device. So this is an example of how you can actually handle such a block device. You can specify a command line option in Linux when you boot it, and it will carve out a section of physical memory on even a regular desktop system to be used as a persistent memory device. That persistent memory device will survive reboots, but it won't survive the power off condition. So you can actually simulate persistent memory on your desktop if you wanted to, and you can even reboot the system. It is safe, and you will have the contents available afterwards. So this is a poor man's version that can be used for development purposes. And so what happens then is you get a dev PMEM0 device, which is this is a raw block device. It's like any other, like you would have your hard disk. You have this block device there. And you can then format that thing, let's say, with put an X4 file system on there, and you can mount it. And if you specify a special option here, -o-DAX, it will enable the direct access method on that file system. Once you've done that, this thing behaves like any other file system that you want to have. And all the existing operations work on it. It's just much faster, since the system can go directly to memory, and it doesn't need to go via PCI Express. You can then also specify the DAX option when you mmap a memory area from a file on that file system. What happens then is that the system no longer uses a page cache for that, for the pages in that file system. Instead, you map the pages directly from your non-volatile volume into a user space. And with that, you have the performance characteristics that you want. You can directly modify the contents of your non-volatile volume from user space, and it directly is changed on the device itself, on the NVDIMM device. So this is the easiest way to use non-volatile memory currently on Linux. And you are using a file system in order to make sure that there is an entity in the system and it makes sure that all the consistency requirements are addressed. File systems have been designed with the ability to maintain a consistent state on disk. And we're using the same methods now to maintain a consistent state in RAM and the persistent memory volume. So this is the magic of DAX, direct access. So mmap establishes the references directly. And so also this memory is not, since it's not in the page cache, it cannot be evicted. It's persistently there. That's also one concern that I've often heard from many who are concerned about memory. I don't want the scanning, I don't want the eviction from memory. This allows you to do that. If you want, you can just specify a command line option, and you have this simulated disks, and you can even do that without actually having physical persistent memory. And then, since this is not subject to eviction, the 4K limitations on the page cache is not valid for the DAX volume. This means you can avoid the transactional look-aside overhead that comes with having lots and lots of these 4K pages. You can use two huge pages to directly map the memory from the DAX device to main memory. That avoids the overhead significantly that is needed by the processor to access memory, and allows you a huge window of access to these memory regions without having to go through TLB faults. So this is a significant performance enhancement. So the NVM challenges. We, among the kernel developers, we really want you to use file system semantics because this is very safe. And we know Linux has been running for this for decades, and we know that the way to make sure that the system is coherent is well established. If you want to bypass this thing, then you have additional challenges because you need to work on ways to make sure to push the contents back to the persistent memory storage, because portions of this could be cached in any of the CPU caches. That causes issues with consistency. This is the NVM design. I think we saw this already before. So you have the block device that's underlying everything. There's the additional direct DAX path via the MMU mappings. And there's a file system in between. And the file system can decide on its own if what you're doing there is safe or not. There may be situations in which the file system takes the MMU mappings away and just uses a regular page cache because you're doing an operation that would result in an inconsistent state and where it cannot guarantee that the data is consistent on the NVM device. So the good old daddy of the operating system is around and makes sure everything is safe. And we are preserving the physics semantics as much as possible. So now, this usually only works when you have the operating system take control of the memory, and it has these page descriptors for each 4K segment. The problem with non-volatile memories, it can be very big. And so the amount of these descriptors can be very large. And in particular, on a regular Linux system with 4K pages, 2% of all memory is set aside just for these control structures for memory. So the kernel can manage if the page is consistent with its backing storage, if the page is up to date, if it's locked, if it's just reserved or something, right? So if you add a storage array of 6 terabytes or so, you have to dedicate either an extensive amount of memory to the state maintenance of this memory, or you can avoid that by saying, okay, I don't want to have the state maintained. But then the operations that you can perform on this memory are limited. So there's a configuration option where you can say, okay, I want this non-volatile volume, and I want this to have the operating system state maintenance or not. If you don't want to have that, then there are a number of limitations. In order to maintain this array, we have created another zone, which is called the zone device. The zone device is simply used to describe a memory area that is not under the control of the OS and allows the OS to keep state of all these pages in that range that's external to the OS RAM area. So, and the RDMA subsystem requires the maintenance of state on each of these pages. If you register an memory region, it needs to lock down the memory, make sure that certain operations can't occur from the OS. That requires the metadata structures from the kernel. If these don't exist, you cannot do RDMA to it. So if you avoid the metadata allocation, then you can do RDMA on these things. There's work in progress to maybe avoid that and to maybe make that work, but right now this is the situation. So not all of persistent memory is RDMA-able at this point. Then another thing that was added in the last few years is heterogeneous memory. This is now the situation. You have an accelerator. The accelerator also has its own memory that has different performance characteristics from your main memory. And it has also a connection to you. And now you want to manage memory that's in both. You need to have access to the same memory area in system memory and from the accelerator. The only thing that you have is a PCI Express bus. Both sides have their own page tables. And in some way, you want to be able to share pointers between both areas. And you want to be able to kind of co-process back and forth between the various heterogeneous systems. It is heterogeneous memory because we have two different processor architectures here that have different aims, and they are communicating via a common memory area. So we are creating a unified virtual memory address region on both, so that both processors can see the same memory range, and they can actually exchange pointers because they are valid within the same virtual memory area. So this is all based on the evolution of the MMU notifiers, and it's built on the heterogeneous system architecture standard. The MMU notifiers were first introduced a long time ago in order to have better support for RDMA and other things, and they now become much more versatile with this. This allows you to manage large memory for our devices like GPUs with a common address space. Now you have memory that is behind the PCIe boundary, and memory that's in front of the PCIe boundary. And the heterogeneous memory subsystem manages copies of that. It ensures that there's a vital copy only on one side of the boundary. So a page can be migrating back and forth between in front of the PCIe boundary or behind the boundary in the GPU space. And shared copies, read-only copies can exist on both. And this is used to optimize the latency of access. And the HMMS guarantees you that it synchronizes the view of memory on both sides. And this is another use case for zone device. Zone device describes the metadata structures that the kernel has, and which describe the view. Which page is on which accelerator, or is it on both? So the RDMA issues coming with that one is RDMA only works in a single address space. If you want to do an RDMA on an address space described by heterogeneous memory, then we need to make sure that all the data is first on one side of the boundary, and then we can run an RDMA operation on this. And typically, the pinning with HMM ensures that. The system will then move the memory in such a way that it is on the pin side. And at that point, the accelerator can no longer obtain exclusive ownership of these pages and cannot write to it anymore. So there are certain restrictions that come with this scheme. How much time do we have? What?
8 minutes.
8 minutes, okay. Feature types of memory. This is what I dream about. Maybe we can do something like RDMA squared. Maybe if we can have the whole operating system exported to another one, we can come up with a kind of a shared operating system that's running on both machines. So maybe that's also a different way to look at persistent memory pools. All right, what we want in terms of the employer where we just work for, we want to have a remote RDMA for large storage arrays. So some way to access a large storage array without any software in between. So the client should be able to just figure out where's the memory and automatically do an RDMA operation into the storage array. And the storage system should be completely shut out of that. That is probably possible with something like PNFS with RDMA layout. Some of our core kernel developers are working on this scheme right now. And this would allow us to access large arrays of NVMe devices with minimal latency. Then the NVMe memory pools are probably something similar, and maybe that we can also get to that with that kind of approach, but I'm not quite sure what the benefits of that would be. Ultimately, what we need is a multi-layered approach to memory. Right now, we have a very complex storage hierarchy. We have the top portion of the caches and main memory that follow one semantic, and then we have the storage layers, which follow a different semantic. And the persistent memory is in between, and we're not clear what we should do with this. Sometimes we follow the upper layer, and then we follow the lower layer. It would be great to have a unified description of memory layers where we can add arbitrarily new memory layers depending on the performance characteristics. Even in the storage layer, we have issues. So we have very slow disks at 100 meg. We have faster disks. And there is also a tiered approach going on there for some reason. Some vendors offer you faster access tiers that then propagate down to slower tiers. If we had something like a unified storage hierarchy that allows consistency and persistence across all these layers, that would be very helpful. Right now, what I'm seeing is we're developing these things at various levels, and we are ending up with a lot of details that are only working on a certain layer. And that makes software development and the use of the storage hierarchy extremely complicated. You always need to be aware of the particularities of this new layer. I think with DEX, we have found with the file systems a good compromise. But if you really want to get into the details on low-level programming from user space of these persistent regions, then you're getting into a lot of very detailed issues that will be very time-consuming. So that's it. Any questions?
Christoph, you were talking about transparent huge pages. What's the cost of migrating all that data around?
Yeah, that is significant. Well, the question is, this transparent huge pages, they are generated on the fly by the OS, trying to figure out if there's adjacent pages in a process. This is pretty expensive. So what happens is there's a process running in the background that scans all processes in the system and figures out, is this all populated? And if it is, it tries to then do the migration and things. So this has been, at least for our use cases, I'm an HFT guy, you can't have this happen during trading. So what we do is we manually trigger a pass of this THP correlation at the beginning, before trading begins. So half an hour before, we run all our machines through this mechanism. It correlates all these things, makes sure that the huge pages exist. Then we forbid anything, and then trading starts. So you can target this at various places where you can afford this. Maybe if you start an FHPC job, make sure all the bindings are loaded, all the data's in memory. Then you run one process, and it gets all very fast. And then you stop this, and you just run.
Can you please come up to the mic? Thank you.
When you mapped to reduce TLB use for the DAX file system, how did you control or guarantee that it was laid out correctly in the first place?
You can, how does this work? I don't remember exactly, but I think you should be able to specify map huge when you do the mapping to a DAX file system. That would be the logical choice. I'm not sure if that's actually the case. Any other questions? Otherwise, I'm done. Thank you.